Well, I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to just bless this class today, Lord. In your name I pray. Amen. So I'm sure some of you have questions about the reversal of a path. That maybe you're stuck on that homework question. Probably be good for me to spend about 10 minutes of class talking about some options we have for a given parameterized curve. And then I'll get back to the integration stuff. But there's something perhaps left unsaid that I should discuss. So suppose we have a path that goes from here to here, let's say. I don't know what that is, but we could talk about the parametrization R going, let's say, from AB to this curve C, right, which is a subset of R2, right? So the initial point, we could say that the initial point P was equal to R of A, and the terminal point Q would be R of B in this setup, right? If I was to pick a particular point in between, right, say here, right, then I could look at the velocity vector would be something like this, right? dr dt at some point time t, let's say, where what? This time is what? Somewhere between, it's somewhere in the domain of the path. It's somewhere in AB. All right. So one thing you could do here would be to define another. You could reparameterize. We could reparameterize this path. All right. So we could talk about, say, R2. All right. We could talk about R2, which is a function of S, let's say, and where so here, oh goodness gracious. So let's say that's R. Oh, curses. I have decision-making problems. R2 of t, let's say, is R minus t. But I don't want to use t because let me say s instead of, and the reason I want to do that is because this s, well, let's just talk about that. So here, this minus s would be equal to the t, which is an element of AB. So in order to plug minus s into the input for the path, I would need that this minus s is between A and B. All right? So what does that say? That says A is less than or equal to minus s is less than or equal to B. Right? So what does that say about the input variable s for this R2 I'm defining? Can you, the inequality which I'm about to underline in green, can you tell me how to, what does this say about s? If I multiply this inequality by minus 1, what happens? It reverses the inequality, right? And this will give us minus b less than or equal to s less than or equal to a, minus a rather. So therefore s is an element of minus b to minus a. So what I'm trying to explain here is that, you know, the path S maps to R2 of S, this describes reversal of path with new domain, right? What's the new domain? Minus B to minus A. Now, I've had some conversations with a couple of you about this problem where I've used T for both the path and the reversal. But it occurred to me, maybe if I introduce another letter for the parameter of the reversal, it might be helpful. It might be clarifying. So that's what I'm trying at the moment. Now, let's see here. So in terms of R2, what is this? So this, like, R of A is equal to what? It's equal to, in terms of the reversal, what is it? It's R2 of what? R2 of minus A, right? And what's this? This is equal to R2 of minus B. And how about the midpoint? If I look at this T, that's this, well, let me use yet another color here. This point right here, right? This point is what? That's R2, excuse me, R of T, and that would be equal to what? R2 of what? Negative T, but yeah. In other words, S is equal to minus T. And what we expect is that dr2, we expect that this right here, I mean, for a specific example, you could work it out, and this should be something like dr2, let's say ds, evaluated at s equal to minus t, all right? It should be the reversal. Let me look at this for a specific example to try to make it sink in better, okay? Let's look at R of t equal to, I don't know, t plus the cosine of 2t, and then t cubed. And let's say this is for 0 less than or equal to t less than or equal to 2. All right? I want to find reversal of path with domain minus 2 to 0. All right? So using my current notation, we would define R2. What would the reversal be? I'll use S. So it's supposedly R of minus S, right? So I have to set T equal to minus S. And what does that give me? S, oh, I can't do math. Minus S plus the cosine of minus 2S, comma, minus S parentheses cubed. Can we simplify that? I think we can simplify it a little bit because cosine's even, right? So this is minus S plus the cosine of 2S, comma, minus S cubed. No parentheses because the minus pulls out of the cube. So there you go. That it would be the reversal of the path that's given in this example. So if we wanted to compare the path and its reversal at a given point on the curve which is parametrized, we wouldn't compare s equals to t, right? If we want to compare, we're stuck with, we could look at it this way, right? I mean, this is saying when we plug in s into the reversal, we have to plug in minus s into the original path to compare, right? They don't meet up at the same parameter input. They meet up at opposite parameter inputs, given this setup. So what's dr dt? Dr dt here, the velocity of the given path is 1 minus 2 sine of 2t, 3t squared. What's the velocity of the reversal using s instead of, instead of t? Dr ds, what is that? Okay, fine. I mean, maybe I shouldn't think of t and s both being time. Let's say that they're the parameter of the path. So this would be the tangent vector to the path at s. So that's supposed to have a 2. Oops. So what would that be? That would be, I got a minus 1, minus 2, sine 2s, and minus 3 s squared. What? I heard a question. Was there a question? Uh-huh.
So we went from in the reversal formula, we went from a negative 2s cosine to a positive 2s.
Yeah.
How did you go to that then?
Oh, cosine is even, so we can absorb minuses into the argument of cosine. Yeah. It's because cosine's an even function. Other questions?
Why is it not negative 2s over the side?
Which one are we talking about?
At the bottom. Negative 2 sine 2s.
Don't I have that? Minus, so the derivative of this with respect to s is minus 1, and then cosine differentiates to minus sine, and then the 2 from the chain rule. Okay. Now, yep.
So on the top, when you simplify cosine negative 2s to cosine 2s, you carry that over when you take the derivative of that? Since sine's an odd function.
I don't know what you mean.
So when you went from cosine negative 2s to cosine 2s because cosine's even,
Yeah.
when you take the derivative of the original
Uh-huh.
vector r2,
Right.
you I guess go straight from
Well, so
2s to
I'm not, maybe this, I'm differentiating with respect to s to get down to there, right? This guy is coming from up here. Does that clarify it? Yeah.
How would you prove that dr dt and its reversal are opposite at a point?
I'm getting there. So, yeah. So we'd like to compare tangent vectors of the path t maps to r of t versus s maps to r2 of s, which is the reversal. This notation I'm using right now is yet another language for expressing what a path is. What is a path? A parametrization of a curve is a mapping. You take the parameter in, you output the vector, right? This is what a parametrization is. It's gluing points along a curve with a dependence on the parameter. So you can tell when you glued each point on the curve according to what the parameter is. You think of it that way. So this would have velocity, if you will, v of t would be dr dt, right? This, on the other hand, would have, let's say, v2 of s which would be dr2 ds. To reasonably compare these, I shouldn't compare them at s equals to t. That wouldn't make sense, right? So to compare them, we should compare v of t versus v2 of minus t, right? Or what's your other option? Equivalently, you could compare what? You could compare, if you're like, well, I'd rather compare it as, you could also look at v of minus s versus v2 of s, if you want to think, if you want to use s instead of t as being the primary thing to compare. I mean, either one of these would be a legitimate pair of things to compare, because those would be the velocities attached at the same point, right? Okay, so this is a reasonable comparison, remember, because r of t is equal to r2 of minus t. So when I plug in t into the original path, when I plug in minus t into the reversal, we're looking at the same point on the path. All right, getting back to my example, what's dr dt? There it is, right? 1 minus 2 sine of 2t, 3t squared. Versus what is v2? Well, what's dr2 ds evaluated at s equal to minus t? What's that equal to? Plug in s equals to minus t. What do we have? We've got minus 1 minus 2 sine of 2 times minus t, comma, minus 3 times minus t parentheses squared. So I just plugged in s equals to minus t into the velocity of the reversal. Now what is sine? Is it odd or even? Odd, right? So this is minus 1 plus 2 sine of 2t, comma, minus 3t squared. Notice that the minus is squared, it goes away, right? And what can you tell me about the velocity of the reversal here? Do you see it? Compare this versus that. What's the relation? What's that? They're opposite signs, right. So you could factor a minus 1 out of this one if we wanted. You could say, well, that's minus 1 times 1 minus 2 sine 2t, 3t squared, right? Which would be precisely this one. And this holds for every t, right? And correspondingly every minus t equal to s in the domain of the reversal. This is one approach to the problem, yeah. Oh, it doesn't mean anything. It's just, I use the angle brackets when I'm thinking of a vector. I tend to use the parentheses when I'm just thinking of a point. But we identify the vector from the origin with the point. So don't read too much into it. It's just I have assumed the two are the same thing for so long, it's hard for me not to do it. There is a version of calculus where I always make a distinction between these objects, and I teach you that vectors can be added to vectors and points can't be added to vectors except in a certain context, blah, 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 blah. And I started writing notes on this perspective once, but then I found that it was very, very, it led to a lot of extra talking about points in vectors, which wasn't particularly helpful. And the other reason I shouldn't do that is there's many other courses where this identification is made. And so if I make a distinction there, then it puts you at a disadvantage when you get to other courses where we just add points to vectors and things. So that's my rationalization for confusing the two. Yeah?
For the drdt that's reversal, if s equals
Why does 1 become negative 1? What do you mean?
From DRDT to reversal.
This?
Yeah.
dr2 ds down here is right here, and I got that from differentiating R2 of s. So that minus 1 came from derivative of minus s being minus 1. Yeah.
Just the little U with a line under it.
The little u under with a line.
Less than.
Oh, yeah, this one?
Yeah.
Very good. That means subset. Right. So like R2, that's a little bit too small for R2. But R2 is, it's the whole plane, right? The curve is something in there, so it's a subset of it. It just means that the curve lives in R2. Every point in the curve is a point in R2. In Calc 3, you'll talk about paths which live in R3, for example. 3 dimensions. Other questions? So let me ask you guys sort of a design question. What if you want R3, all right, R3 to be a mapping from AB to the curve that I'm talking about. Let's go back to the abstract generic curve to discuss things again here. Suppose I want to find an R3, which is also a parametrization of the reversal of the curve. But notice the difference. So the sort of knee-jerk reversal, the one that's simplest for me to just throw out in passing is, oh, you just changed t to minus t. You guys accept it. You only come to terms later with the fact that if you do that, that means that you've messed up the domain in some sense, right? The domain has gotten swapped around back to minus b to a, right? What if I want a reversal such that the domain is still AB? So what I would be saying there is I'm going from the point P equal to R3 of B. Let me restate that. I'm going from the point Q, which is R3 of A, back to the point P, which is R3 of B. What would the formula for R3 be? All right, so R3, let's use another letter. Let's say lambda equals to R of what? I need some function to put in there that outputs. I want, what do I want? I want lambda equal A when t is equal to b, right? I want lambda to equal to b when t is equal to a, and maybe we can say lambda is something like mt plus some constant c2. Let me say, yeah, something like that. Maybe we can make a linear. Maybe we can lambda a linear function of time, and that'll be enough to find this thing. So this is a design problem. Can you tell me? What should I put in the parentheses there to make this happen? I'm telling you we could use a linear function of lambda to achieve this goal. Hey, instead of using lambda, I used x here, would that make it better? There you go. But keep in mind that that doesn't have to do with the x, which is the geometric x corresponding to the curve. But I don't know, maybe that's helpful to you. I don't know. Oops. How about this? Would this work? What if I did B oh, excuse me, the other way around. Let's say A plus, no, that's not going to work. How about B plus 1 minus x times A? Would that do it? Would that work? What if I plug in x equal to A? What happens? If I plug in x equal to A into that formula, it gives me what? Well, that's not going to do it. I mean, if I plug in x equal to 1, it gives me what? It gives me B. If I plug in x equal to 0, it gives me what? B plus A. Well, that's not it either, is it? Well, that didn't work. All right, so we have B equals to MA plus C2. And we have A is equal to MB plus C2. Can you guys solve these two equations in two unknowns? Solve for M and C2, what do you get? So this was a guess, it didn't work. Right, we're looking for x as a function of t. I think a linear function will work, and it swaps b and a. X equals ab over t is not going to do it. Solve this for m and b, c2. Tell me what you get. If I subtract these equations, what's it give me? We get b minus a equals to what? M times a minus b, right? Therefore, m is equal to b minus a over a minus b, otherwise known as minus 1, right? M is minus 1. And then plug that into either one of these. Like we've got b is equal to minus a plus c2. So what's c2? C2 is apparently b plus a. So what I find then is x is equal to minus t. Oh, you might have told me this a second ago. If you did, I'm sorry. It looks like minus t plus b plus a. Therefore, we can say R3 of x, which I don't like, but you guys liked it, so I'm just sticking with it for a second, a plus b minus t. And I'm not supposed to put that, not minus t. What was I supposed to put there? Oh, phooey. Well, I shouldn't have let you guys talk me into this x business. I think I've got the x and the t. I really, oh, phooey. I wanted to have t. They're supposed to be reversed. Words. I just want these sentences to be reversed. I want t equals to a to imply x equals to b. And I want t equals to b to imply x equals to a. Of course, that's what I've done, right? I just wrote them in the opposite way. So it's kind of stupid, but it is that, right? Because the larger point was I should be saying t equals to mx. But I think so. I get a is equal to mb plus c2. I get b is equal to ma plus c2. I think those are the equations I just had written down anyway. Okay, so long story short here, we get that R3 of x is equal to a plus b minus x by this below. Or AKA what I should have written 10 minutes ago. We could just say R3 of lambda is R of A plus B minus lambda. Or we could even say R3 of T equals to R of A plus B minus T, and that would be okay. Why would that be okay? I mean, if T has a reserved meaning as the parameter of the original given curve, well, we can think of this as being the same T. Where does R3 of T and R of T meet? Like, do we, in fact, you can try it out. R of T is equal to R3 of T, I think. That's not true. Dang it. I mean, there you go, right there. That's how they're related. What's it boxed already? That's R3 at time t is R of A plus B minus T. Yeah.
My only question is, when you put A and B, like MB plus C2,
Yeah.
how did you determine that formula exactly?
This is an educated guess that maybe we can make a linear change in the parameter to fit what we want.
You chose the equation of a line.
Chose the what?
The equation of a line, so M
Yeah, right. Because I want to, if I'm going to use the same, domain, and I just want to reverse the curve, maybe I can just, use a linear change of the parameter, and we can do that. With this, if I was to compare, so all right, what would R of T be equal to? So this is quote unquote T, right? Perhaps it's helpful to say that this is, let's say S instead of T. So if this is S, right? Can you solve that for T? So R of S is apparently R3 of A plus B minus S. But that's true for S between A and B. So, sorry, I've spent entirely too much time on this. What I wanted to communicate to you is you could choose different domains for the parameter of the reversal if you want to. Right? But if we do this, if I was to pick a point in the curve and I want to compare the velocity of the given path to the reversal, I wouldn't compare at t and minus t, right? I would have to compare it something more interesting. I'd have to figure out, if I plug in a given time here, well, what should if I plug in time t here, then I have to plug in time A plus B minus t into the original path. And I would compare those. But anyway, I've said far too much about this already, so I'm going to stop. I'm going to stop. Any questions about homework before I get back to the actual thing I was supposed to talk about today? Aye. Oh, man. Don't breathe that stuff ever. It's not good.
Relations in the form of an addition.
It's that?
In general, should we try to keep the relations between the two?
It's okay.
R3 and R, try to keep the relation in addition.
again, it's just a choice. I mean, you could make the reversal of the curve go faster. You know, you could look for some sort of like, you know, quadratic in time that would go the other direction and make it go faster, or variable speed. There's infinitely many different reparametrizations of a given curve. I mean, there are literally infinitely many choices for how you lay the parameter down on a curve. So this is just one choice. I mean, I can't say more than that. I mean, to me, it's kind of like, the main reason for doing this was just to maintain the same domain for the reversal. That was my motivation here. It's that. Here, let me just, one example and then I'll really stop. Suppose we want to parameterize from here, from P to Q. What did we say that the parameterization was of that? It was P plus T times what? Q minus P, right? For what? 0 less than or equal to T less than or equal to 1. What if we do the same trick, but instead of going from P to Q, we go from Q to P? What does that give us? Let me call it R3. R3 of T is equal to what? We just interchange the roles of Q and P, right? So this would actually be an example of what I just did. So the line segment going from P to Q, the original path, R of T. The reversal of the path, R3 of T, but notice that the domain is still 0 to 1. Right? This wouldn't be like the R2 I have on the board. It would be an example of the general thing I did with R3. Now, I mean, we can work this out a little bit. So if I'm right, what should we be able to check for my example? I mean, what I'm saying is what's A, what's B, and can we verify the boxed equation relating this path and that path? And yeah, the velocity, you're right, the velocity should be opposites, right? Is there a time dependence to the velocity in either one of these? Like, what's the velocity for the first one? Let's just call it V. What's dr dt equal to? Differentiate this, you just get Q minus P. Let's call V3 dr3 dt. What do you get when you differentiate this with respect to T? P minus Q. These are easy. This example is easier to understand than my first one because there's no time dependence to the velocity. Like this one I've half erased now. There was a time dependence. So like you actually had to evaluate at T versus minus T to compare. Here that doesn't happen because the velocity is just, we can just directly say, oh, it's minus, right? So since I'm this far in, so let's look at this formula. So A equals to what here? 0, B equals to 1, right? So just to exhibit this again, what is R of 0 plus 1 minus T, right? So that's R of 1 minus T. If we plug in 1 minus T into R, what's that give us? P plus parentheses 1 minus T times Q minus P, right? So I'm evaluating the given path, replacing T with 1 minus T, right? It's function composition. What happens, can you see how this simplifies? What do we got? We've got P plus 1 minus T times Q minus 1 minus T times P. Does anything cancel out here? Let me just multiply it all the way out. So you got P plus Q minus TQ minus P plus TP. Well, the Q, it looks like the P and the minus P cancel, right? And we can factor Q out. I mean, there's a Q. And then there's a T, so I can say plus T times what? P minus Q. What is that? That's exactly R3 of T, right? So again, this is just an example of what I've boxed, which is to say that, yes, we can reverse the curve by replacing T with minus T, but if you want to maintain the same parameter domain, there is something else you can do, which is A plus B minus T. All right. I'm sorry, I will try to confuse you about parametrization some more some other day. I'll stop for now. Enough suffering. I would rather not. Ah! Does anyone know any kind of like time travel I could do to like get that last 20 minutes back? I mean, this is an important thing for us to actually talk about because you guys will. Implicit substitution. Yay, finally something easier. So here's our goal. Remove radicals or other indesirables via appropriate trigonometric or hyperbolic substitutions. Sounds like some sort of government policy when stated in this form, right? Doesn't seem very kind. All right, anyway, let me show you an example. Example 1. Integral of the square root of 1 minus x squared dx. All right, well, we don't know how to do this integral to start with, all right? Integration by parts, you can try. I don't think it goes anywhere. You can try U substitutions. Good luck, all right? So really, anyway, we need a new method, all right? So trig substitution's the one to go with. Now, when we think about trig substitutions, let's think about it. We've got, let's just, reminder here, we got cosine squared theta plus sine squared theta equals to 1. We also know that tangent squared theta plus 1 equals to secant squared theta. We've also got this to work with, right? Cos squared theta minus sinh squared theta is 1. And I suppose hyperbolic tangent squared theta minus 1 is equal to hyperbolic secant squared theta. Reminder. We should keep these in mind as we go forward here. So when I see this, here's the spark, here's the inspiration, is that I can change 1 minus, first of all, what do you want to do? How can you get rid of a radical is one way you could do, right? Let's see here, example. If I had square root of, 5 squared minus you know, 4 squared, and I rewrote that as the square root of, oh, that's the square root of 3 squared, right? Because everyone knows that 3 squared plus 4 squared is 5 squared, right? But then what's the square root of 3 squared? This shouldn't require thinking, right? 3. Now you're like, well, that's lovely, but I could have just done that that's 9, so the square root of 9 is 3. So like, I'm not very impressed by your example. Fine. You don't have to be a jerk about it. But that's the motivation, is like if we can convert whatever's under the radical into a square, then we get rid of the radical. So that's the overriding goal, is to convert whatever's under that stupid radical into a single squared term so the radical goes away. Right? Or it could be that there's an addition in a denominator such that we want to convert that into a single term so we can just divide it out. That's later. So the idea then is, that's the goal. If we set x, though, if we set x equal to, say, sine theta, what does that make 1 minus x squared equal to? Yeah, 1 minus sine squared theta, which is otherwise known as? Yes, cosine squared theta. What's dx equal to? Cosine theta d theta, right? And so there you have it. This is the integral of the square root of cosine squared theta, closed radical, and then cosine theta d theta by this trig substitution. But the square root of cosine squared is cosine, yeah? So that gives us cosine cosine, which is cosine squared theta d theta, which we're like, oh, we learned how to do that yesterday, right? So that is 1/2 integral of 1 plus cosine 2 theta, which we integrate, gets us a theta over 2, plus 1/4 sine of 2 theta plus a constant. Is that the answer? Well, no. Now we need to go back and put our answer in terms of x, right? So this would be, what's x equal to? Excuse me, what's theta equal to? Yeah, if x is equal to sine theta, I heard then theta is equal to inverse sine of x. Right, and that's kind of like the answer is going to involve inverse sine of x. That's kind of the best I can do for the first term here. 1/2 inverse sine of x plus 1/4 times the sine of 2 times the inverse sine of x plus a constant. So this is an okay answer. It's pretty good. We can do a little bit better. We can do a little bit better here. We can actually take the term I'm about to underline in red, and we can rewrite that as an algebraic function. What's an algebraic function? What's an algebraic function? This is going to be really profound, so, hold on. The algebraic function is a function whose formula is put together by the rules of algebra. In other words, sums, products, roots, divisions, a finite sequence of algebraic steps. Is inverse sine an algebraic function? It is not. This is an example of something which transcends algebra, therefore it's a transcendental function. How on earth can I write sine of 2 theta as an algebraic function, though, here? Well, let me show you. So remember that 2 sine 2 theta is what? Oh, wait a minute. There's no 2 here. What is sine 2 theta equal to, rather? What's that identity for trigonometric identity? I heard a 2. I got a sine theta. I got a cosine theta. Right? So sine and... Oh, wait a minute. Sine theta is what? Sine theta is x, right? And what's cosine theta here? We actually saw that going from here to here. Well, okay, fine, it's not. All right, you can't see it. Let me write down the triangle so you can see it better. Here's the triangle of the substitution. We got our theta. Sine theta is equal to x, right? So that means there's an x on the opposite side. There's a 1 on the hypotenuse. And when you make this picture, which represents the substitution we're making, what's going to happen is the one thing that's not directly given by the substitution. It'll always be the thing you're trying to get rid of, which in this case is the square root of 1 minus x squared. Yes. Thank you. Adding drama. I like it. Yes. Ah, trigonometry. So this is a known trig identity. But once you know that, the cosine is the square root of 1 minus x squared. Right? So if we divide this by a fourth, what does it give us? We get a half, right? X times the square root of 1 minus x squared. And that's pretty much the best answer I can give here. So, I try not to talk about the test too much, but just to give you a distinction. Because the next question you guys are going to ask me is, so are you going to take off points if we don't do it like is boxed in the black? That depends on the instructions. If the instructions say, calculate the integral and leave the answer in algebraic functions as much as is possible, right? Then what's in black is the correct answer. What's in blue is strong partial credit. All right? What's in blue is always strong partial credit. It's exactly correct if I don't specifically say leave your answer as an algebraic function. Okay? That's the rules I set in here. Other people just assume that you have to do it as black as best, but I want to say that specifically because it does take a little bit of extra work to convert it back to an algebraic function. Yeah. Example 2. All right. Example 2. Suppose we have the integral of the square root of something like x squared plus 8x plus, I don't know, 17. Dx, of course, right? No, dx equals incorrect. Dx is not optional. It has to be written there. As you can see it, I will take off points if the dx is not there, yes. By the way, I called this an implicit substitution. The one other point I should make in example 1 before we even go on. Why is it an implicit substitution? We're changing the variables. We're making a substitution of integration variable, right? We're going from what? From x to theta. What's the new variable? Theta. So before we make a u substitution, we do what? We write down like u equals x squared. Or u equals, sine theta or whatever. Well, but the u sub, we have u equals to stuff in original variable, right? A trig substitution has a rather different structure, right? It's old variable, equals to sine or cosine or cosh or sinh or tanh of the substituted variable. And that's why it's an implicit substitution. When we say implicit in math, that means that the new thing we're defining, it's not just outright stated. It's somehow wrapped up in some kind of relation. All right? This is the meaning of the word implicit. So how about this one? How do I do it? Day one, like first thing I talked about, yep. Complete the square. So complete the square, what do we get here? So this would give me an 8x, an x squared, also a 16, right? But I've got 17, so I'll put a 1, right? All right. So I want what's under the radical to become a square. There are sort of two natural choices here. Okay? So these trigonometric identities, let me write them down again. A little bit different. So one thing we have is that cosine squared theta is 1 minus sine squared theta, right? We can also solve that for tangent squared theta equals to what? Tangent squared theta? Yeah, secant squared theta minus 1. We've got secant squared theta is what? Yeah, tangent squared theta plus 1. And how about the cosh and sinh? Yeah, cosh squared theta equals sinh squared theta plus 1. And what else? If I solve for tangent squared theta, oh, that's kind of the same thing. Forget about that. How about, yeah, sech squared, hyperbolic secant squared. That's what? That's tangent squared theta minus 1. So these are some patterns we should keep in mind. So there really are two contenders for this in the substitution as you look at the patterns, right? What are the two contenders? So yeah, okay, so like this or like that. And so let me call this star, let me call this star star. So either we could think about x plus 4 equal to secant theta versus, that would be star, or x plus 4 equal to the hyperbolic sine of theta.
It would be tan, right? X plus 4 equals tan theta.
Nope. See, because you're trying to make the sum of the squares become, you got it, yeah. I know, it's, yes. So, choose your adventure. What do you guys want to do? Star or star star? Star star. Hey, you guys chose wisely. Because if you chose star, that leads us to the integral of secant cubed. That's no bueno. So, yes, if we make an x plus 4, let's make this our substitution. X plus 4 equal to hyperbolic sine of theta. Then in that case, x plus 4 squared plus 1 is what? Sinh squared theta plus 1, which is equal to? Cosh squared theta. All right, so that's great. So first of all, the thing under the radical will just become hyperbolic cosine squared theta. Yay. How about dx? What's dx here? I heard a what? Cosh d theta. Very good. So yeah.